everybody. Thank you for coming to today's webinar. As you can see, today we're doing geometry. So the plan will be to do about 45 minutes geometry. I do want to cover some things on triangles. I want to do some things on triangles inscribed in circles. So do a bunch of different stuff. One thing as these webinars start to grow and then there's more people attending, which is awesome. It's just more people who may be unmuted during the webinar. So if you notice that you're not muted, just do me a favor and mute yourself, because otherwise it's loud for the other people. And other than that, we can get going. Oh, one kind of exciting piece of news that may help some of you here if you're still debating between GMAT and GRE. We did just recently launch our GRE site. So if anyone is interested in the GRE and you're thinking of possibly switching, that is an option. If you know anyone taking the GRE, certainly let them know. I'll put the link into the chat, but it's super exciting. We're happy to have it, and we're looking forward to it being equally as successful as what we've done with the GMAT. So with that said, I want to get into the first question. For those of you who have been here before, you know the drill. I'm going to be giving questions. I'll give everyone a few minutes to answer the questions. And then when you're done, you can put the questions or your answer rather, in the chat box. And from there, I'll be able to see what everyone's getting, and then we will go over the solution. So the first question I want to do is a pretty cool question, testing you on really lines versus angles in triangles. And this is a type of question that they can throw at you in many different ways. But this is one very interesting particular way in which you can see it. So again, give everyone about 2 minutes, and then we can chat about the result. I'm not sure why someone just stole a ball from me, but I stole it back. Okay, here's the first question, everyone. As I said, put your answer in the chat box so we know what's going on. So that was roughly 2 minutes there. This is a great question because one of the things with triangles is that the angles of a particular triangle correspond to a particular side of a triangle. So to be a little bit more detailed about what I'm saying is, in this problem, we are given that x is the smallest angle in this triangle, which means that BC has to be the smallest side. We're also given that y is the middle angle, which means this has to be, for lack of a better word, the middle side as far as length, and then this has to be the largest side. So the minute that we know that AC is 10, and the minute that we know which corresponds to the largest, or is the largest side, and the minute that we know AC is, BC is actually 6, the minute we know BC is 6, we know that the middle side has to be between 6 and 10. Now, we're not told that the sides have to be integers, but we can see our answer choices are in integer form. So the possible middle side is between, and we'll just call M for the middle, is going to be greater than 6 and less than 10, based on these angle measurements. So that gives us possible options. Now, if we take the 10 and 6, that's going to give us a total of 16. So if we subtract 16 from each one of these Roman numerals, we get a possibility of 6, we get a possibility of 8, and we get a possibility of 10 for the middle side. And what we can see is, since M must be between 6 and 10, the only logical option here is 8. That corresponds with number 2, and that is answer choice C. So they can test this in a variety of ways. You know, be prepared to see it in a variety of ways on this exam. But, you know, this is like anything else, and I say this every week, that, you know, we're in a situation where if you know these small rules, you're going to get to a question like this, and you're going to immediately have a process of how to deal with it. Flip side is, if you don't know these rules, you get to a question like this, and let's say you don't have a process immediately of how to solve it. So what I want to do next here, just getting in another question, is I want to do another interesting problem that deals with triangles. Sometimes they're gonna try to trick you on where the height is of a particular triangle. Now, I wouldn't say that this problem is the hardest problem in the world, but I would say that there's definitely some ways in which they're trying to trick you or trap you here into thinking, you know, what the height actually is of the triangle. So when everyone's going through this question, do a really good job of making sure that you're finding the height versus the base and stuff like that. There's a lot we can talk about once we go through this question. So I'll give everyone about 2 minutes and then we can go from there. Okay, let's get after this one here. I do see a lot of correct answers here, which is good to see. So what's kind of going on in this question is the idea of where to find height in a particular triangle. And one of the things to understand is the height, really in any polygon for that matter, but it's more kind of front and center within triangles, is the height has to be perpendicular to the base. We just take that for granted when we look at, say, a rectangle because, you know, the width is perpendicular to the width, or the length, or if you look at a square, the side is perpendicular to the side. You never really actually have to think about it. In a triangle, these exams are forcing you to think about it. So in this particular instance, first and foremost, there's a lot of information. We need to fill that in. So we have DE is 8. We have BD as a whole is 20. We have that CD is 3/5 of 20. So 20 times 3 over 5, that gives you 12. So if CD is 12, I'll change the color, means BC is 8. Now, question is saying, that was telling us that BD is parallel to AE, which is important. And we need to know what the triangle is of ABC. So we need to know the area of this triangle here. Now, the interesting part is that the height is not AC. Some people may think it is. They may be trapped to think it is. They may think DA is the height. But really, the height is DE. And if you were to basically slide this over, this is the equivalent of DE, and that's going to be 8, and that's also your height of this triangle. So the height, I mean, another way to look at it too is that the height can be, I change the color, the height can effectively be here, but it doesn't really matter. The point of this question is that the height doesn't necessarily have to touch the triangle that it's the height of, it simply has to represent it. So if we see that the height is 8, and the base is 8, since the area is 1/2 base times height, we have 1/2 times 8 times 8. The answer here is 32. It doesn't look like too many people fell for that trap there, which I'm happy to see. I do want to get into one other type of problem, another rule that I'm not going to, well, actually, let's hold off on that. I want to get into some inscribed shapes since we have about 25 minutes. So what we're going to move on to doing here is we're going to start off with circles, central angles, how those work, and then I want to deal with triangles inside circles. There's a lot of inscribed shapes that are asked about on the exam. One of the most popular, in my opinion, that you'll see a lot of, has to do with triangles inside of circles, as far as I've seen on this test. But before we even get there, they do like to test a lot on central angles and things like that within circles. So I want to talk about central angles and how they relate to arc length, and I want to talk about central angles and how they relate to area. So the first question we're going to do is here. Give everyone a few minutes and then we can chat. Okay, so this is testing a very interesting rule here, and what that rule is has to do with how a central angle in a circle is proportional with the arc length. So what you'll notice here is it's saying the center of the circle is at point O, which means this 30-degree angle here is considered the central angle. So there's a really great proportion that exists anytime you have a central angle within a circle. So you can say that the central angle, which I'll label CA, is 2/360 as the arc length, and when we say arc length, that just means a kind of fractional component of the circumference, is to the circumference. So, again, so central angle is the 360 as arc length is the slope. All very important stuff to know. Now we have to actually fill in our values. So we know what the central angle is. It's 30. We know that the total degree measurement of the circle is 360. We don't know the arc length, which is obvious because they're asking for it. And we have to determine the circumference. Since segment XO is 12, we see that that's the radius. Remember, circumference is 2 pi r. So circumference is 24 pi. That and that. Now, one of the things I always say to do, and it doesn't matter, where you're at in the test, you always want to look to reduce. You want the numbers to be as small as possible at all times. So 30 over 360 actually will reduce down to 1 over 12. So we can say 1 over 12 equals x over 24 pi. Cross multiply, 24 pi equals 12x. X equals 2 pi. And there is our answer. So this is a great thing to have tucked away, everyone. Central angles, you know, they love to ask about them. There's a lot of kind of variations they can do with this stuff. And remember, this can also relate to when we have inscribed angles in these circles. Right now, we're really only talking about central angles, but as we get into inscribed shapes, we'll start having to deal with inscribed angles. So we're going to get to that, obviously, before we end. Here's one other question I want to do. This deals more with sector area. So we'll give everyone another 2 minutes, and then we can discuss. Sorry, everyone, I just was muted. So now I will say what I was saying again. This is going to be pretty much the same proportion that we use. The only difference is that this here is sector area, this here is total area. We are given a lot of the same information from the last problem, but we need to use it in different ways. As an example, XO is still the radius, but to get the area, we need to do pi r squared. So the area becomes 144 pi. So if we do this out in full, we see that we have 1 over 12 is equal to A over 144 pi. If we cross multiply, we get 144 pi equals 12A. Divide everything by 12, and A equals 12 pi. So the answer here is B. So now we get to get into what I was talking about before, which is inscribed shapes in circles. There are going to be some slight changes. cool things I can teach you about as far as relationships go. But one thing you always want to keep in mind is you're always looking for the bridge between one shape within the other shape, meaning there has to be some sort of shared side in order to be given information about one shape and then asked about the other shape. Now that might seem convoluted. Obviously, I will explain myself further once everyone dives into this question here. Give everyone about 2 minutes on the clock. Okay, so about 2 minutes there, a little longer. So this is an interesting question. What's going on here is we have a triangle inscribed in a circle. Now, one important note is that if you ever have a triangle inscribed in a circle, and one of the sides of the triangle looks like it also represents the diameter, which in this case xz does, then the diameter is equal to the hypotenuse. So what does that tell us? Well, it tells us that in this case we do have a right triangle. Now it's kind of obvious as well because we know that this side is 30, this is 90, this is 60. So in fact, we're dealing with a 30, 60, 90 right triangle. That's helpful because one of the other things you're tested on here, as everyone knows, is the ratios between 30, 60, 90 triangles. That ratio, 30 to the 60 to the 90 is x root 3, and of course 2x. So with that said, we are going to go through and take some of the information provided and then use it to our advantage. So we know that the triangle is inscribed. We talked about that. We know the circumference of the circle is 10 pi. Why is that important? Because we can take the fact that we know the circumference and use it to get the diameter. Since pi d is equal to circumference, which is the same thing as 2 pi r, we see that the pi's cancel, and we see that this is equal to 10. So effectively, if 2x is equal to 10, it's opposite the 90-degree angle, x, of course, is equal to 5. So that's the side opposite to 30. And then simply, side opposite to 60 has to be 5 root 3. So area is 1/2 base times height. 1/2 times 5 root 3 is 25 root 3 over 2. So hopefully that wasn't too bad for everyone. I do want to do a slightly harder question that deals with arc length right now, and this has to deal with arc length wrapped up in inscribed shapes. So everyone take a look at this. Do another 2 minutes and then we'll go. Okay, so it was about 2 minutes, and this is another solid question, which is testing obviously inscribed shapes, which we can all see. We're given, once again, that XYZ is inscribed in the triangle. We're given right away that the triangle has a hypotenuse of 18. So you're seeing that the diameter is also equal to 18. Now, because we know it's 30, 60, 90, we can then say, okay, well, the side opposite of 30 is 9, and the side opposite of 60 is 9/3. So similar to what we did last time. The last component of this question, though, is it's saying that the length of arc XY is what we're looking for. Now remember, that's arc XY. What you'll notice is that that arc is opposite a 30-degree inscribed angle. Because it is inscribed and it is not central, the proportion slightly changes. And it changes to doubling the inscribed angle. Just because we don't necessarily have the time, I'm not going to get into why. You can definitely read about this, though, on Geometry Chapter. But you can memorize if you double the inscribed angle, set it over 360, then you do the same thing. We care about arc, we'll call x, over the circumference, since the diameter is 18. Circumference is 18 pi. We know that 30 times 2 is, of course, 60, so we end up getting 1/6. Sorry, that should be 18 pi. We get 1/6 equals x over 18 pi. 6x equals 18 pi. X is pi, there's your answer. So last but not least, I want to do another type of question here that shows triangles inscribed in a circle in a slightly different manner. Actually, not really inscribed, but in a circle is the best way to put it. And give everyone a few minutes, and then we will wrap up with this question here. Okay, so this is another interesting question. The one thing you'll notice is that the triangle is not inscribed as a circle, but there are two equivalent side lengths because they're both radii, QR and QP. So the area of the triangle is 72. We know that PQ and PR are the same length. Thus, we're dealing with a 45, 45, 90. So all we really need to do is set up our formula, x times x over 2, which is the area of a triangle, equals 72. X squared equals 144, or x equals 12. Now, since we know that x is 12, we know that 12 represents the radii of the circle. Since the area of the circle is pi r squared, simply saying pi times 12 squared, which is 1.5. So this was a little different change up from what we were doing earlier. I think this is another great question that shows triangles and circles. And I hope everyone got a lot out of what we did today. I may do a second geometry webinar next week. I'm going to decide what I feel like doing. But nonetheless, we'll come back to geometry at some point. And as always, I really thank everyone for coming here today. And as I did at the beginning, the GRE site is live. So if anyone is looking for GRE help, it's just at gre.targettestprep.com. And as always, reach out to Scott and I if you need anything. So thanks for coming, everyone. See you next week.